Our today's speaker is Dr. Semere. He is postdoc at chair of Vibro-Acoustics of Vehicle and Machines at Technical University of Munich at Stefan Marburg Group. And today he will talk about acoustic metamaterials for impedance matching. So, Semere, before I'll give you the floor, should we ask questions during the talk or after? What would be better for you? We don't hear you. You're muted.
During the talk or after the talk is fine.
Okay, nice. Then we can start. Semere, please.
Yeah. Thank you for the introduction, Maria. And so actually this is a title of which I did my PhD 2 years ago, I would say. So it is about the application of acoustic metamaterials for enhancing impedance matching. In this project, actually, we tried to develop an acoustic metamaterial that to enhance transmission through. The first idea is to enhance transmission through metals for non-destructive evaluations. Then we also applied for medical ones. So I will try to discuss this one in more detail. And then, for example, in transducers, or as when the wave is generated by the piezoelectric materials, then actually it passes through the air or different layers of materials, and this actually there is a large amount of impedance mismatch or reflection presence during this propagation. It means reduced reflection or reduced transmission means the image quality or the target detection quality will be lower. So the aim is how does we increase the transmission so that we can enhance the imaging or detection, for example, for tumors or for non-destructive application, in also for various applications. Traditionally, I'll say there are different approaches. For example, the most common ones are using quarter wavelengths, which by designing by having the material to just a mean of for example, this two materials that we want, and we can design transmission or perfect transmission at narrow boundaries. However, if you want to increase the boundaries, we have to have more layers, or 3 or 4 layers, to increase the boundaries. So this is actually one of the disadvantages of these methods. For example, in upper megahertz frequency, it becomes more complicated to manufacture and to integrate this kind of quarter wave layer impedances. So in the last few years, acoustic metamaterials have been developed, and these methods actually they have shown a number of applications. For example, negative density bulk modulus, and just a near zero effective density, which you all are familiar about. So there also have been there's been a development in various applications. For example, for acoustic limitations and acoustic cloaking, hyperlinks, and like a wide range of applications have been discovered by using these acoustic metamaterials. So the concept is how does we develop acoustic or impedance matching layer using this technology or this acoustic metamaterials. So we proposed in 2 ways in general. So the first one is using external cloaking, I would say, in general, and there is by manipulating wave propagation paths, and we can design. We can use this acoustic metamaterials to design to work as impedance matching layer based on these 2 ways. So first we see how we use this external cloaking works. So when we say cloaking, I think you also are familiar about it. Basically, it does not depend on the material property. It does not. Basically, it involves about how to deflect the wave or go around the material rather than through the material. So this kind of cloaking actually doesn't help in the applications of metamaterials or in such kind of practical applications. And so there's a concept of external cloaking, which we consider the material properties or the mechanical property of the material, for example, the impedance, the density, and then we can design complementary acoustic metamaterials that can cancel the reflection from that material. So I will discuss this one further in detail in the next few slides. And so when we talk this external cloaking, actually, researchers has come up by combining two different independent mechanisms that we can achieve transmission. For example, let's say we have a negative density and a negative bulk modulus. For example, negative density can be achieved by periodically arranging the membranes, as you can see it here, and negative bulk modulus can be achieved by periodically using this side holes. So as you can see here, below the cardiac frequency, there's no transmission at all for both the negative density and for the negative bulk modulus. However, when we combine them together, we can get a moderate amount of transmission due to this double negativity. So how can we design such kind of things and what other approach can we use? This is what we try to investigate in this research. So our first idea is, how do we use this Helmholtz instead of these side holes? How do we use these Helmholtz resonators? Helmholtz resonators are well known for their absorption characteristics, not their transmission characteristics. So basically, they used widely for just absorption. So, but what makes them interesting is they also form, they also have a band gap. Maybe we can use that band gap to design such kind of, or what we call complementary acoustic metamaterial. So first, we use theoretical model to analyze the plate lumped model theory to analyze the negative density or the periodic arrangement of the plates. And as you can see here, the effective density can be approximated based on this equation, which is using lumped model approximation. And to compare this lumped model approximation with the numerical simulations, this formula or actually can be used just to approximate the effective density of the periodic arrangement of the plates. And we assume actually the plates are have constraint or they're not moving at the boundaries. And similarly, we used Helmholtz resonators. The same way we calculated the effective bulk modulus, or we can also the inverse of bulk modulus, which is compressibility, and using this lumped model and then the finite difference approach model. And then we compare these two models, how do they capture the principles of this kind of structures. And so you can see it here, both structure for both methods, this analytical and the simulations actually captures the principles really well in the given frequency range. So as you can see also, we can see along X and along Y direction, which we simulate independently, and negative density has been observed, as you can see it here. And also for the bulk modulus or the compressibility, you can see they also approximate really well. They're in a good agreement between these two methods. So our next approach is, how can we design such kind of or complementary acoustic metamaterials from these structures? First, we have to investigate their transmission property. And their transmission property, as you can see it here, independently simulating of the structure. For example, for the plate and the Helmholtz resonators, as you can see it here, the plate have actually lower frequency range around 31 kilohertz, the cutoff frequency around 31 kilohertz, and the Helmholtz resonator have transmission deep around 40.5 kilohertz, which is around resonance frequency of the Helmholtz resonator. So this actually, you can see that at this point, at this frequency, there's no transmission or there's no transmission at all. So when we combine them together at this particular frequency, we get a transmission or a full transmission, as you can see here, so that it becomes more transmission rather than opaque. So we can say that these transmissions act, this metamaterial, the combination acts like it can transmit sound wave through their structure. And then we'll further also investigate what how this numbering the number of unit cells actually affect the transmission property. So it means like if you increase the transmission or the number of unit cells, as you can see here, the amplitude actually increases and the bandwidth becomes narrow. But we use 9 unit cells for this case, so we actually expect around a moderate amount of transmission. And then we choose our target material. And then, for example, for medical application, like I said earlier, is we choose a skull layer. So this for skull layer, it has a material property given with density of around 2,000 kilogram per meter cube, and with speed of sound, which is given around 2,500 meter per second. Based on this Acoustic coordinate transformation theory, we can actually use this material property and design inverse of the material property, which is a complementary one, by using these equations. So basically, we assume that the CMM or the metamaterial width is equal to the width of the metamaterial, and the width or along y-axis actually becomes half of the metamaterial, half of the target material or the skull layer. So by substituting these equations, actually, we can get along x direction, the metamaterial should have at least half of the negative density of the material or the skull layer, and along y-axis, it should have negative twice of the density of the material that we try to investigate. Similarly, also for the bulk modulus. So based on this, we go to the graph or to the effective material property, as you can see here on the left side. And at the given frequency range, for example, along x direction, it should be at least around 1,000 minus 1,000 kilogram per meter cube, which is approximately given in this red line, dotted line. And along y-axis, we expect to be around minus 4,000 kilogram per meter cube, which is given in this dotted line, which is rho y. And based on these equations, actually based on this, we can say that actually this complementary, we have developed some complementary metamaterial at certain frequency level. So here, this is the full wave transmission by using the metamaterial, and we use perfectly matching layers at the end to reduce reflections. And then we get at least 83% transmission by using the metamaterial. And without metamaterial, we got around 32% at all. And even though these methods are attractive, but one of this limitation is that we need a control environment, and also this in submillimeter dimension actually become more complicated to manufacture it. And another one is they work in a single frequency range, which means their applications limited. So how does we increase their boundaries is our next goal. So this is why we consider by manipulating wave propagation wave paths, or the wave propagates inside the metamaterial. By modifying that, we can actually broaden the bandwidth of the transmission. So a number of researchers have developed a method to increase transmission, for example, through these metamaterials. For example, using impedance matching layer or gradient layer structure, also by developing a periodic arrangement of structures, we can actually increase the transmission boundaries of these metamaterials. However, we can see that in order to increase transmission, at least we need a periodic arrangement, or at least 2 or 3 periodic arrangements of metamaterials. So our goal is how we can use this a compact or a single unit cell metamaterial, and that can cover a broader boundaries. So this is one of the goals of this research. So next, we developed the concept, or we developed the design, which we call this helical structure with helical hole. And this is what we call, this is the modified, the left side is the modified, the unmodified structure, and the right side is the modified structure by connecting these two helices together. And this is the red shows the propagation of the wave through the helica. And we consider actually this is in water environment. So it's an ultrasonic, the upper ultrasonic range. And as you can see here, the structures have geometrical within sub-millimeter or just smaller dimensions. So it becomes more complicated to manufacture. More I'll talk about how this we can manufacture these kind of things. And then we further analyze how does we describe this in terms of effective material properties. Since you can see that it's at least 5 times less than the material, the wavelengths, at least effective material property or approximation works in this region. So here we use effective material property to approximate its property. And for example, the refractive index can be calculated by dividing the acoustic wave traveled divided by the thickness of the metamaterial, which is shown in the top right section. And also the effective diameter and effective perimeters can be calculated accordingly, and which can be substituted to calculate the effective refractive index. At the same time, given the transmission equations, and when we say there is a transmission peak, which means that this term should be actually equal to pi and multiples of pi. So it means that we have transmission peaks or a unity transmission, we get unity transmission. And also we get transmission dips when this term becomes to multiples of pi over 2 or just odd multiples of pi over 2. And by substituting this equation actually on the left side of the equations, we can get the minimum transmission equals to, we can describe its minimum transmission according to this equation. And from this equation, actually, we get the effective density. We can calculate the effective density. And just simply also for the other metamaterial, for example, considering transmission peaks, the effective just refractive index can be calculated basically just assuming n equals to 1, and then just simply substituting, we can get the refractive index, which is lambda, is actually the wavelengths here. So we can actually represent this 3D structure in a 2D one. So next, we did actually compare our approximation model with the 3D model. And this is the 3D model that we use actually. Yes? Okay. I thought, does anyone have any questions? No? Okay. So we have this model, and this is 3D model, which we apply cloaking boundary condition along y in the axis, and there we have this perfectly matching layers at the end of the metamaterial, at the end to reduce reflections. And then we also have, we represent a 2D structure that have effective density and effective refractive index calculated by previous approximations. And as you can see here, we get a good approximation of the metamaterial or the model by using this effective medium approach. However, it fails, or not fails, but it's less effective around the higher frequency regions because it becomes, the metamaterial thickness becomes larger than the wavelengths, and effective medium approach fails in that region. Still, we can say that it captures the principle well in this frequency range. And then what happens if you combine these two materials together? For example, like earlier I said, having combining multiple structures or periodic arrangements can result in broader boundaries. What happens for this structure is then our next we investigate it next. And then as you can see here, this is for the unmodified structure. This is for modified structure of the transmission bandwidth. And you can see at least the modified structure is at least approximately 4 times greater than, it has 4 times greater bandwidth than the unmodified structure by simply connecting the the helices together. And further, we investigate by applying two, for example, this is for unmodified structure, the left side, and the right side is for the modified structure. How does this varying the gap or changing the gap affects the boundaries of two periodic materials? And as you can see here, actually having two or three structures does not actually bring any significant effect on the boundaries. So in general, we can say that the single metamaterial performs well compared to this twice two metamaterials or periodic arrangement of metamaterials. So it makes it compact and also broad bandwidth in the given frequency range. So how does this happen is how does this mechanism work? So in order to further investigate, we just did simulations, which is using acoustic, velocity, intensity. As you can see it here, assuming that we have two ports that the wave propagates, and considering that they meet at the junction region. So we observe that the acoustics actually travels in different directions. For example, this is for lower frequency in the given range, and this is for higher frequency in the given range. So actually the waves are propagating in the counterclockwise direction, as you can see it here. So why would this happen, or how could this why would this happening is our next we try to investigate this one. So our assumption is that, for example, for assuming this wave propagation from 1 to 3, we will call it length 1, 3, and we assume it's traveling in the negative d directions, and so we expect this kind of equation. And also from 2, 3, we expect propagating in the positive d direction, and this is what the equation. And at the junction, we expect these two waves to sum up and get this the wave lag, or they can have a phase advance or phase lag based on the frequency or the wavelengths of the materials. So this one of the assumption is actually when the frequency becomes larger on the upper range of the frequency, we can expect that this is the shorter distance. It means that it takes it travels more to the right. It means more momentum will have it will have more momentum to this direction, to the positive z to the negative z direction, and it creates such kind of effects such as going direction in counterclockwise direction. However, for lower frequency regions, when L13 L23 is greater than L13, and we expect the wave to propagate in just normal direction, which is in negative in positive z directions. So this is actually to explain how this wave propagations actually can be different in a given frequency range, even though we get a broader bandwidth. So to further provide an experimental setup, we in order to verify our concept, we did an experiment, and we use hydrophones, as you can see it here, and we use waveguides. We designed a waveguides, which and actually this is since we assume it's a rigid material, and we use metal, which we manufacture using 3D technique, which is called selective laser melting. And based on that, after field signal processing, we get the absorption performance of this unmodified structure and the modified structure, and assume that the metamaterial dimension of the whole size is like 1 millimeter and 0.6 millimeters. So this manufacturing this kind of things actually has become more complicated, or I'll say precision is it's not that in detail in that kind of frequent sizes. So there's slight discrepancies in the between the numerical methods and the experimental methods, as you can see it here. However, we can still say that it can capture how it works, or how can this metamaterial represented, even though there's slight variations in terms of amplitude or resonance frequencies. And in one of other authors also discuss about such variations in experimental and with numerical for subwavelengths or subwavelength holes. This can be explained in terms of discrepancy of measured transmission coefficient with higher. Just we didn't consider this evanescent higher order diffraction exciting at the grating interface in the hybrid or the effective parameter approximations. And then our next approach is, since not only broad bandwidth, how about their angular property, or what happens if there is an oblique incidence? So in order to capture this, we did actually, this is numerical simulations. And as you can see here, both the unmodified and the modified structures can work well in until 60 degree or 50 degree of the incidence angle, which compared to state of the art, which propose at least, as you can see here on the right side, it works well, or we can say it has a broadband range of incident angles. So we can generally say they have broad bandwidth, compact, and also broad angle characteristics. So in general, so we concluded that when we use this external cloaking methods, actually they are perfect for impedance matching layer with third medium, which involves another medium, but they require higher precision manufacturing and controlled experiments. For example, the tension of the membranes or the plates should be controlled precisely, and also if they are actually can be done, it's very attractive for a medical imaging application because they can capture the evanescence wave presence in the vicinity of this material. In terms of this wave path manipulations, we can say that actually, basically, we are dealing with impedance matching between the background medium, which can be water or air, and with the metamaterial performance, which does not include another third medium. And so still there's, I would say, it needs a little bit of research by using third medium, how this behaves. And also there are fairly straightforward applications, which are they are compact in size, and also they have broadband characteristics. And as I said earlier, we just need further modification to transmit between sound between three different mediums, for example, by just incorporating this kind of structure between transducer and, for example, between the scale layer, so we can increase more transmission, or we can enhance the transmission through this structure. So this is that's it actually. Yeah, thank you for listening. Yeah.
Great, Semere. Thanks a lot for a good talk. I think we've got a lot of questions for you. Does anybody want to start? Maybe my question will be first, and it's in general. First of all, could you tell me, is there any rule for design of unit cells? On some slides in the first part, you've shown how it was designed. Yeah, maybe here, yes, so somewhere there.
Yeah.
Is there any rule?
No, there's no rule actually. We use trial and error method on this one to develop such method, and we actually tuned this the range to work in the frequency range that we intended to work. So actually, there's no general rule, I would say.
Mm-hmm. And Sergey, could I ask one more question?
Yes, please. Yeah.
Semere, and is there any frequency limitation for this technique? For example, would it work in megahertz range or just in kilohertz range or something like that?
So it actually is working in kilohertz range, actually, which is actually in a middle frequency or ultrasonic frequency range. But if it's an upper frequency range, it means the holes dimensions should be much more smaller. Creates more complexities during manufacturing, actually. And also in terms of there are other effects, for example, thermoviscous and other kind of effects will have a significant effect on the transmission performance of the material. So I would say, yeah, it depends on the frequency range that we try to investigate. So we can tailor the properties of the structure to fit to the frequency range that we want to design.
Thanks. Sergey, please.
Yes, so thank you for the talk. Actually, I do not really understand how exactly this design work, because basically, as far as I understand, you just increase the wave propagation path.
Yes.
And it seems that if you increase the path, so you should also increase the associated losses. And in this sense, the transmission should be lower. Yeah, so could you please maybe explain once again how this structure helps to increase transmission?
Yes, actually, the one you mentioned, principle, we use it for sound absorption, for example. If we increase the length, and by the dissipation actually will create some losses, and then we get some smaller dimensions or smaller transmissions. However, in this case, actually we can say that the design structure, like on the previous slides I showed you, where we have a number of lengths or structures where we have Fabry Perot resonances. And these Fabry Perot resonances can actually create transmission peaks or high transmission peaks. So this actually can be used along with, actually you can see that it is near a quarter wavelength, which is around 4.1. And we can, based on these combinations, along with constructive and wave interference, then we get this broader boundaries using such structures.
Yeah, thank you. Actually, on the slide 24, where you show this angle-dependent transmission, so there are also, it seems like kind of equidistant peaks. So is it also related to some geometry of the structure? Am I right?
So could you please repeat it once again?
So here on these maps, so the yellow color shows the transmission near 1.
Yes. Yes.
And there are kind of the central peak near 1. Oh, it's like I don't see the. Is it in what units? It's like at the center of the map, and then at the left and on the right from this peak, there are also this transmission near 1. Yes. So is it also some kind of geometry-related resonances, or why they are seems like equidistant? So is it kind of like Fabry-Perot resonance?
Yes. Actually, it's like I discussed earlier that Fabry-Perot resonances actually occurred. For example, let's see this one based on these equations, and so we multiples of pi. When happens at multiples of pi, then we get this resonances. So based on that, we get a periodic arrangement, periodic resonances, I'll say. So that's why we have this this kind of transmissions. Actually, if you compare them, you can see that this is the lower one is the modified one. You can see that it has more broader transmission in the given bandwidth or in the given frequency range compared to this upper ones. So I would say it is due to this peripheral resonance that happens, this kind of things. Yes.
Yeah, thank you. So may I ask one more question?
Yes, please. Yes.
Yeah, so regarding the previous method, so when you show this structure for skull, in the system, maybe slide 14, so in the numerical simulations, you show that you have the layer of water, then the structure, then skull, the question is, so if you consider like I mean, real life applications, so you will not have water before the structure. So what happens if the first layer will be just air? So will you have some reflections from the structure?
Yes, actually, it depends. So we have to treat as different impedance, but we use water because it assumes it's the properties or the characteristics of lead. It's much more related to that one. So that's what we use these waters that can approximate how the density and speed of sound. But if you can for practical applications, actually, there is no water. It's basically transducer. Then there is maybe a gap, or there is a couplant, for example, and then there is base skull layer. So totally a different concept if you talk about the practical applications, but not. No, I don't think it works for practical applications in this way.
Yeah, so thank you very much.
Yeah, thank you.
Guys, any other questions? Okay, then Semere, thank you. And I have just one question, maybe a bit stupid, but on slide number 10, how did you compare the parameters of the electric circuit and the acoustic parameters? Are there any like generalized procedure of this?
Actually, it depends on the geometry of the metamaterial. So based on the geometry of metamaterial, we can actually represent in terms of inductance or in terms of capacitance. For example, if it's a short tube or something, you can represent as inductance, and vice versa. If it's like Humboldt emitters, then you can say it's capacitance, something like that. And based on the geometry, we can calculate their resonance frequencies and related parameters.
Oh, okay, thank you. So, any other questions?
Looks like no questions else.
Okay, then Semere, thank you for your talk.
Thanks a lot. Thanks a lot.
Thank you for having me here. Yeah.
It was useful for us. So then we should finish for today, Andrei.
Yeah, we can finish here.
Yeah, okay.
Thanks a lot. See you sometime, Semere.
Bye.
Bye.
Thank you.